recall, in our last lecture we had talked about how to obtain the canonical sum of product and product of some representations of a function from the truth table. So, we continue with our discussion in this lecture as well. We shall see that not only from the truth table, even from a given expression, we can systematically apply some algebraic manipulation technique to obtain the canonical expression. So, let us try to look at it and see that what kind of transformations are possible. So, the title is obtaining canonical representations of functions. So, we first look at the algebraic procedure. So, what is the algebraic procedure? So, what you are saying is that for a given function, let us say I have a function of, let us call a b c, a function of 3 variables a b c, and in this function I have one term, let us say a b, or something else is there. You see, this is certainly not a min term because c is absent. So, what we are saying is that for all missing variables, you multiply the product term by that variable plus its complement. The reason is very simple. If you multiply them out, it will be nothing but a b c or a b c bar, just like this, right. So, this same rule is being followed here. You see, here we examine each term of a given sum of product expression. Well, if it contains all the variables, that means it is a min term, do not do anything. But if it is not a min term, some of the variables must be missing. So, for every missing variable, let us say x I, multiply that term by, as I said, x I bar plus x I. Then using the algebraic rules, you multiply out all the terms, and finally, you will be getting a sum of min terms. Some of the min terms, some of them may be repeated. So, you eliminate the repeated ones, redundant ones, and what you get will be your canonical sum of product. Let us take an example here. Consider a 3 variable function given like this. So, here you see the last one is obviously a min term, all the variables are there, but the first product term c is missing, the second product term both a and c are missing. So, for the first one, what we do? We multiply it by c or c bar. For the second one, we multiply it by both a or a bar and also c or c bar. For the last one, we do not do anything because all the 3 are there. Then you simply multiply them out, a b bar c, a b bar c bar, and here you multiply them out. I have just skipped the steps. See, a c and b, a c bar and b, a bar c and b, a bar c bar and b. So, I have multiplied all of them out and a b c is there. Now, you see which of them are repeated. You see this a b c is appearing twice. Other than that, all are unique, there is no further repetition. So, you write down the expression, you have 6 true min terms, 6 min terms, and this will be your canonical sum of product expression. So, given any expression, you can apply these rules to expand the function, and using this Boolean multiplication rules, switching algebra rules, you can obtain the sum of product expression. Similarly, let us look at the reverse, product of sum. Product of sum means, here I am saying, let us say again, let us take an example, a function of 3 variables a b c. Suppose I have a term a plus b and something else. Let us look at this one. This is certainly not a max term, because C is missing. So, if C is missing, what I do? I add a term C C bar to this. This I can do because C C bar is nothing but 0, end of a variable and its complement. So, anything odd 0 does not change the function, but if I do it, then I can apply the distributed law A plus B plus C, A plus B plus C bar. So, I can write it as A plus B plus C and A plus B plus C bar. So, now I have the max terms. This is the basic idea here, okay, right. So, let us see. We examine each term of a product of sum expression. If it is a max term, we do not do anything. If it is not a max term, then you look at all missing variables, and for every missing variables you add the term xi xi bar. Then as I said, you can apply the simplification rules and distributive laws to obtain the sum terms, and you see if any of them are redundant. If they are redundant, eliminate them. Let us take an example. Suppose I have a function like this, where there are two sum terms. The first one contains only A bar, second one contains B bar and C. So, what I do? For the first one, B and C are missing. So, we add B B bar, also C C bar. The third one, A is missing. So, we add A bar. Now, after doing this, we apply the distributed law. So, here we have skipped a step again, these two things we are showing in a combined way. So, A bar B C, A bar B C bar, A bar B bar C, A bar B bar C bar. So, there will be 4 terms generated, and for this one B bar C A and B bar C A bar, one of them is repeated. I am just eliminating the repetition. So, I am only showing the final form. No, sorry, here there is a repetition. Let us see which one is repeated. A bar B C is 1, A bar B C bar, A bar B C bar is 1, A bar B bar C, yeah, A bar B bar C is repeated. Okay. So, you just use only one copy of it, other one you delete, and you get the final form here. This is your canonical product of sum expression. So, you see that means even using algebraic technique, you can start with any given expression and you can find out either the product of sums, product of max terms, or sum of min terms. Both of them are canonical expressions, okay, of a function. All right. Now, let us see how we can transform the forms from one to other, sum of product to product of sum, or product of sum to sum of product. So, I shall show you one, the other one you can try out with examples. Here the idea is to repeatedly apply De Morgan's law, De Morgan's theorem. The idea is this: say a given function, if you complement it twice, the function value remains the same. So, our idea is the same, like intuitively I am telling you, if I have A B or C D, and if I complement this once, what I will get? If I complement this once, I will get A bar plus B bar and C bar plus D bar by 2 applications of De Morgan's law, you can see. Then we are doing another complementation. Let us see what you are doing this. Let us take an example. Let us take an example. Suppose I have a given sum of product expression like this. This is a canonical sum of product expression. So, you consider that this is a 3 variable function. So, if I consider the truth table, so how many rows will be there? There will be 8 rows. Out of these 8 rows, 5 of them are 1. The output is 1 for 5 of them. These are the combinations. So, what I am saying that the function will remain the same if I complement it twice. Okay. So, f bar, this was f. So, within the inner bracket f bar whole again bar. Now, let us look at what is the meaning of this inner thing, some function bar. So, what this function represents? This function represents these 5 rows of the truth table for which the output was 1. Not of that. What is the not of that? Not of that means the remaining 3 rows which was 0. So, if I take the not of this, instead of algebraic manipulation, I can do a shortcut. I can simply look at which of the rows are not there. See, a bar b c was not here, a b c bar was not here, and a b bar c was also not here. So, if I want to complement this, we simply consider the remaining minterms. It is same as this. So, you can verify, you can also complement it, do a lot of multiplications and simplifications, you will be arriving at this form, but here we have done a shortcut. And finally, this again there is a not, the last not here. So, if you do this, now you apply De Morgan's law straight away. This a bar b c becomes a plus b bar plus c bar plus becomes and a bar b bar c plus becomes and a bar b c bar. This will be c bar, sorry, this will be c bar, fine. So, like this you can convert a canonical sum of product expression to a canonical product of sum expression. Now, see, for this example, the sum of product had 5 terms, but product of sum is having 3 terms. It will be smaller, but it may not be the same for all the functions. For some functions it can be the other way around also. Okay. Now, this we have already seen earlier, let us look at it once more, there is no harm. So, what we are saying is that how to obtain the canonical sum of product expression for a truth table. This I have already shown with the help of an example of a full adder in the last lecture. You consider rows of the truth table for which the output is 1. For each such row, form a minterm, where the literals are defined like this. If a variable is 0, you complement the corresponding variable. If the variable is 1, you leave the variable as it is, do not complement, take the sum. What you get is the canonical sum of product expression. This is what we discussed in our last lecture. Let us work out the example once more, and there is no harm in working out again. Let us take the example of this here. Just to recall what we said, just for the sum, we said that we look at the rows for which the output is 1 and it is 0 0 1, we write a bar b bar c, 0 1 0, we write a b c bar plus 1 0 0 a b bar c bar, and finally 1 1 1 a b c. So, you can straight away write like this, right. This already we discussed earlier. Now, since our ultimate objective is to design this circuit, once you do it, what next? So, can we convert this function into a gate level circuit? Let us see how. Let us write down that expression once more. So, what you saw is sum is nothing but a bar b c plus a B bar C plus A B C bar plus A B C. You see, you have a function. I can straight away convert this function into a gate level circuit. How? I use 4 AND gates, one corresponding to every product term, and the output of all the AND gates I take together and I connect them in an OR gate. This will be my final output. Now, let us look at the individual AND gates. First one is having A bar B C. So, I have a variable A, I use a NOT, A bar, B I connect straight, C I connect straight. So, A bar B C, this output will be giving A bar B C. Second one is A B bar C. So, I connect A straight away, B bar C. So, I have here A B bar C. Then A B C bar, I have A, I have B, then of course, there will be NOT gate here, there will be C bar. This will be A B C bar, and last one will be A B C, no need of any NOT gates here, just connect A B C. So, the point to note is that given any sum of products expression, you can directly convert it into a so called AND OR circuit realization. There will be one level containing only AND gates, there will be one level containing a single OR gate, and in the input you may be requiring some NOT gates, because some of the variables may be complemented, right. So, for this function you need 4 AND gates with 3 input each, 1 OR gate with 4 inputs and 3 NOT gates, right. This is how you can convert a function into a circuit. Similarly, you can do the same thing for a product of sum realization. Here you recall, this also we discussed earlier. We consider rows of the truth table for which the output is 0. For each row, you form a max term where the convention for the variable polarity is just reverse with respect to sum of product. If it is 0, then you use it in uncomplemented form. If it is 1, then you complement and take the product of all the max terms. What you get is the canonical product of sum expression. This already we illustrated earlier with the help of an example. So, for this full adder example again, let us look at the carry. Let us look at the carry. So, here the convention says you look at the outputs where the value is 0 and A, B, C all three are 0, 0, 0. Convention is do not complement them, A plus B plus C. Second one 0, 0, 1, 0, 0 and 1 means you complement. Third one 0, 1, 0, 0, 1, 0 and last one is 1, 0, 0, 1, 0, 0. So, this will be the carry out. Now, again just like a sum of product expression I told you, if we have this kind of an expression you can directly convert this into a gate level circuit, but here it will be different. In the first level you will be using OR gates, there will be 4 OR gates in the first level and there will be a single AND gate in the second level. This will generate the final output. So, the output of the OR gates will be connected here. Now, you see the OR connections. First one says A, B, C. So, you connect A, B, C straight away. Second one says A, B, C bar. A, B and C with a NOT gate, C bar. Third one A, B bar, C. A, B with a NOT gate, B bar and C. And last one A bar, B, C. A bar, B and C. So, you have these 4 product terms appearing here, which you finally AND them together using this AND gate. It is very simple. This is also a 2 level realization. This is called a OR AND realization. Sum of products get mapped into AND OR, but here you get mapped into OR and AND, right. This is the basic convention. So, actually what you have seen is that given a function, you can either convert it into a sum of product expression. From the sum of product expression you can realize the corresponding circuit, or you can have a product of sum expression. From there you can convert it to a circuit. Now, it depends whether you need an AND OR or an OR AND. So, you will have to start with either a sum of product or a product of sum. But one thing you should remember, ultimately our objective is to implement the circuit using gates, and the implementation cost should be reduced as much as possible. So, one simple metric or measure of the cost is how many gates you need. Now, it is not possible to say that which of the two will give you the better solution, sum of product or better, or the product of sum, means AND or AND. So, this depends on the circuit and it varies from function to function. You will have to analyze and find out that for the sum of product how many true minterms are there, are they large in number or small in number. If you see that there are a large number of true minterms, then possibly product of sum will be better, and the converse means also if it is less, then sum of product will be better. So, with this we come to the end of this lecture. In our next lecture, we shall be talking about another characteristics of these gates and these basic functions, and we shall be discussing the notion of functional completeness. Okay, this we shall be discussing in the next lecture. Thank you.